Welcome back, children. Today our quick revision chapter is electromagnetic induction. Let us begin. Electromagnetic induction is the phenomenon by which there is an induced EMF produced at the ends of a loop, a coil. Whenever there is a magnetic flux change associated with it, whenever magnetic flux linked with this closed coil changes with the time, there is an induced EMF at the ends of the coil. If the circuit is completed, that induced EMF generates an induced current. Okay, and that is Faraday's law of electromagnetic induction. Let us see the equation. Mathematical equation for Faraday's law. Faraday's law of electromagnetic induction. It says you that induced voltage V is equal to rate of change of magnetic flux. That is the magnitude of induced voltage. Magnitude of induced voltage at the ends of a coil in a time varying magnetic field is given by d phi by dt, where phi is the magnetic flux. Where magnetic flux phi is a scalar, but it can have positive or negative because it is the dot product of flux density vector B and area vector A. So B A cos theta. If angle between flux density vector and area vector is 0, then the flux is maximum. That happens when the plane of the coil or closed loop, plane of the coil is perpendicular to the magnetic field. That's very important topic. Suppose this is the coil and the coil is in YZ plane. 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 This is Y, this is Z, and this is X. Then the field vector is along x-axis. Field vector is along, flux density vector is along x-axis, and the coil is in YZ plane. Then angle between flux density and area vector is 0 or 180. That is why the flux is maximum. So whenever a magnetic field associated with maximum magnetic flux, the magnetic field vector is found to be perpendicular to the armature coil. Magnetic field vector is normal to the plane of the coil. This topic is very important. Okay, very simple concept, but students used to make mistakes. That happens when theta equal to 0, because theta is the angle which is measured with the normal. That's the reason why students make mistakes. The normal to the area vector is along the outward normal, which is given by the area vector. Direction of the flux density vector is along this line. Angle between field vector and area vector is theta. So angle theta measured between normal to the plane of the coil and field vector. That's it. So when theta 0, flux is maximum, theta 90, flux is 0. When theta acute, flux is positive, theta obtuse, flux is negative, theta right angle, that is flux 0. No flux is linked when magnetic field grazes the plane of the coil. When magnetic field grazes the plane of the coil, there is no flux, but field is there. Flux is not there, then the voltage would be, what about the voltage? d phi by dt. If flux is a constant, voltage would be 0. If flux is time varying, only there is voltage. That is called induced voltage. If flux is time varying, that time varying magnetic flux gives rise to a voltage that is called induced voltage, induced EMF. Okay. If you neglect the resistance of the external circuit, that can be called induced EMF. That can also be appearing as induced terminal PD, that is induced voltage. But if there is a closed loop, it will give rise to a current called induced current. Okay, this voltage equation can also be written in its integral form. Closed integral E dot dl is equal to minus d phi divided by dt. This minus sign is interposed by Lenz, and that law, concerned law, is called Lenz's law. Lenz's law brings that negative sign there. Negative sign indicates that induced voltage is or induced current is always in such a way that it opposes the flux change. Induced current or induced EMF opposes flux change, whatever is produced. So, induced current produced in a coil is in such a way that it opposes the flux change. Induced EMF opposes the growth of current through a coil. Induced EMF opposes the decay of current through this. Whenever there is a change in current, whenever there is a change in flux, whenever there is a change in field, with the time, there is an EMF produced. Okay, that is called induced EMF. And this electric field is called induced electric field. Induced electric field. Induced electric field is not the conventional static electric field. It is not the conventional static electric field. Conventional static electric field is conservative, and work done over a closed path is zero for that. Here, work done over a closed path is not zero. This is actually work done in making unit charge over a round path. Closed loop is nothing but d phi by dt. That work done is the rate at which the flux changes with time. Okay, so induced voltage is equal to minus d phi by dt. That negative sign is introduced by Lenz's law. So Lenz's law is the law, basic law used for finding the direction of induced EMF and induced current. Lenz's law states that induced EMF or induced current is produced in a closed loop whenever a flux change is associated with it, and the direction is in such a way that it always opposes the flux change. That's it. V equal to minus d phi by dt, closed integral E dot dl equal to minus d phi by dt, where phi is the magnetic flux. What is the unit of magnetic flux? Let us see what is the unit of magnetic flux. Unit is Weber. Weber, we used to write WB, Weber, or Tesla meter square. Tesla means Newton per ampere meter. So Newton per ampere meter into meter square, that is Newton meter per ampere. Newton meter per ampere is joule per ampere. That's very important, students. You can easily by heart its dimension. What's the dimension? Joule per ampere, that is ml square t raised to minus 2. Joule. Joule means ml square t raised to minus 2 a raised to minus 1. ml square t raised to minus 2 a raised to minus 1. So that's magnetic flux. Magnetic flux is B dot A, Tesla meter square, Newton meter per ampere, ml square t raised to minus 2 a raised to minus 1. Magnetic flux is a scalar. All that we have discussed now. So this equation can be simply written as minus d by dt of B A cos theta. And this is the basic principle of AC generator. AC generator. So let us revise one of the very powerful application of electromagnetic induction, which is nothing but AC generator. The thought of alternating current was first introduced, presented by Michael Faraday during his famous Faraday's experiments. During that experiment, when performed, he was humiliated by a group of DC propounders. That time scientists were, most of the Tesla, Edison, all these scientists were you during that time very popular, and they were propounders of direct current. They were sellers of direct current, utilizers of direct current. And they started humiliating this person, and by saying that what is the use of this little current? Michael Faraday that time answered, yes, this is a little current. That's right. But what is the use of a newborn baby? Really, it was a newborn baby, and now we use alternating current for most of the industrial applications. We use direct current only for very small current applications. So alternating current has become that much applicable in daily life to common people. And that was laying major stone, foundation stone in the development of each of these countries where they accepted alternating current. That's just history. Anyway, AC generator works on this principle. V is equal to, formula would be minus d by dt of Va cos theta. When the armature coil is rotated in a perpendicular magnetic field with an angular speed omega, the phase angle argument theta can be written as omega t, so that V can be written as Va omega, sine omega t, taking the derivative. Minus of minus become plus. When you take derivative of cos, that becomes minus. For n turns of the armature coil, it can be Ban omega sine omega t. So V equal to V0 sine omega t, where V0 is the voltage amplitude. So voltage is a sine function, but flux is a cosine function. Flux is equal to Ba cos omega t, that is pi 0 cos omega t. So voltage is V0 sin omega t, flux is pi 0 cos omega t. Pi 0 is the flux amplitude, V0 is the voltage amplitude. Flux is leading voltage in AC generator, flux is leading voltage by pi by 2 phase angle. So in AC generator, based on this equation, voltage or flux is leading, but what phase angle? Pi by 2. That's AC generator. Okay. The angular frequency of the AC generated is omega. This all we will be continuing in chapter AC generator for revision. So induced EMF, closed integral E dot dl is equal to minus d phi b by dt. From that, induced voltage equal to minus d phi b by dt. All these equations are very important. Minus d by dt of b dot a. If theta equal to 0, flux is maximum, then voltage equal to minus d by dt of BA. That can be written as minus d by dt of area into dB by dt if area is a constant, but field is varying. So area constant but field is varying, it can generate voltage. Now if B into dA by dt, B is a constant but area changes continuously, area expands and shrinks, closed loop, then flux change thereby produced and produces voltage. Both can be combined together, that is minus of A dB by dt plus B dA by dt. Both the variations can produce by using product rule. B and A both are variables. Then also there are a wide variety of ways in which you can produce flux change, thereby producing EMF. So induced EMF can have these lots of formulae. Now induced current I is equal to, if circuit is completed, it generates induced current, that is given by minus V by R, that is I is equal to minus 1 by R d by dt of flux. Now induced charge dq equal to I dt, so minus d phi b divided by R. For n turns it can be minus n by R d phi by dt, for n turns it can be minus n d phi by R. So these three equations for voltage, current and charge important. Also we have learned about an induced electric field. Suppose you have a closed loop here, closed loop, and magnetic field is directed inward. Magnetic field is directed inward and which is a function of time. Suppose you have a time varying magnetic field. Suppose that magnetic field increases with the time. The external magnetic field what we apply increases with time. This closed loop magnetic field is inward and that is increasing too. Okay, then what is the direction of induced current? That you can find out using Lenz's law. If magnetic field is inward, you by heard this. If magnetic field is directed inward and that inward magnetic field is increasing, you can imagine that there is a north pole of a bar magnet approaching close to this. When north pole is approaching, when a north pole is approaching like this, suppose this bottle, this top portion cap is a north pole is approaching. When north pole is approaching, for opposing the approach of north pole, the nearer face of the closed loop becomes north, for which the current in that coil is anti-clockwise. So current in that coil is anti-clockwise. Anti-clockwise north, then clockwise south. When north pole approaches, anti-clockwise. When north pole recedes, clockwise. Listen, when south pole approaches, clockwise. When south pole recedes, anti-clockwise. Repeating, north pole approaching and south pole receding, anti-clockwise. Okay, north pole receding and south pole approaching, clockwise. You listen to this repeatedly. Okay, I am not repeating. Now this is anti-clockwise. Direction of induced electric field produced by this time varying magnetic field is tangential to that point over the loop. Okay, you can take any point on the loop. You can take any point on the loop and that tangent gives the direction of induced electric field. So induced electric field is forming closed loop. It is not as the conventional electrostatic field. Electrostatic field never forms closed loop. Electrostatic field originates from positive, terminates at negative. But induced electric field never originates anywhere. Instead, it forms closed loop. Okay. Till the discovery of this induced electric field, it was only known about magnetic field lines making closed loops. But electric field also could make closed loop. That was only found after the discovery of this one. So induced electric field is produced by time varying magnetic field that is in closed loops. So it is non-conservative. Work done in one closed loop is not zero. Work done to move a charge over a round trip over this closed loop is given by minus d phi by dt. Okay, that is Lenz's law. So this is very important topic. Okay, induced voltage, induced charge, induced current, induced electric field. Okay, here all these cases we found that the conductor is at rest. The conducting coil is at rest and the magnetic field was time varying. Conductor is at rest. Magnetic field is time varying. This can be also produced by, the same effect can be produced by, as in Faraday's experiments. You can place a closed loop here. The axis of this magnet is along this line. Now the north pole of that magnet is close to the closed face here. Okay, north pole is approaching. Then anti-clockwise current is formed here, due to which a north polarity, repulsion. So north approaches, the coil repels it by producing a closed loop. As there is a closed loop, there is a current. Okay, conductor is at rest, magnet is approaching. That produces a increasing magnetic flux density through the closed loop. That produces an increasing magnetic flux, thereby producing induced current in the closed loop, right? That is Faraday's law. Now, the same result could be produced by fixing the magnet and moving the conductor. Okay, same effect can be produced in a steady magnetic field. Same effect without any change. Same effect can be produced by a moving coil or moving conductor. Conductor is moving in static magnetic field. Okay, then that EMF is called motional EMF. Now motional EMF. When conductor is moving, that is motional EMF. Suppose the conductor whose ends are namely PQ moving in a perpendicular inward magnetic field with velocity V. Okay, this conductor has large number of free electron density, and that all electrons now having a velocity along the direction of the conductor superimposing with the random velocity of those electrons. Random velocity of electrons is there. We cannot determine it is zigzag path, average velocity becomes 0. That does not produce any difference. But what happens? When this conductor is moving towards right, the large number of free electron density of the conductor also moves with that. Otherwise, it will not leave the electrons there and conductor alone moves. It doesn't happen. Conductor takes the free electrons. Conductor when moves, free electrons also moves together. Right? Now, these free electrons are now moving in magnetic field. Lorentz force is acting. Fleming's left hand rule, forefinger magnetic field inward, middle finger direction of velocity of free electron density, large operation of free electron density, thumb represents force on a positive charge. So all positive charges are attracted upward, pushed upward. So electrons are pushed downward. So end P becomes negative and Q becomes positive. Okay, that EMF developed due to the development of an electric field directed from Q to P. Now this electric field is not forming a closed loop. This electric field is not forming, students listen, this electric field is not forming a closed loop. It is the conventional electrostatic field. But still it produces the same effect of electromagnetic induction. But that is produced by a moving conductor in static magnetic field. Here magnetic field is not varying. That's why this electric field is not induced electric field. It is the conventional conservative electric field. Okay, this one work done over one closed loop should be 0. Okay, so we have to develop another formula for which only we use Fleming's right hand rule for finding the direction of this motional EMF. Okay, forefinger still magnetic field, but here thumb represents direction of velocity of the conductor. Middle finger represents EMF. You know, in current electricity we have learned that EMF is a scalar but has direction. -2 plus. So middle finger is along upward. Okay, so direction of motional EMF is upward. Students clear? That is from P to Q. Tell me which is minus P to Q. -2 plus. So P should retain minus. So tallied. The result tallied. And that EMF is given by motional EMF. I am using a different letter. Okay. For avoiding the confusion. That will be BVL. Okay, is it clear? Magnetic Lorentz force we know given by Q into V cross B. Magnetic Lorentz force we have another formula of for a straight conductor I into L cross B. For a straight conductor I into L cross B. Okay, here force is a vector. Q, V, B, three things are there. Q is anyway scalar, velocity field vector. That is why we need to have a vector product. But the problem is that here this EMF is a scalar. V, V, L, all these are vectors. Then how to arrange them to form a product? Here we use that box product. Okay, so comparing with this Q into V cross B, we can write L dot V cross B. This can be the formula for motional EMF. L dot V cross B. L dot V cross B. Okay. L is the vector, V cross B is a vector, then L dot V cross B will be a scalar. That's why EMF is a scalar. So L dot V cross B can be used. You can permit cyclic changes. This L you can move here, then V goes here, B comes behind. Like that cyclically you can write it in three different varieties. So direction of motional EMF, magnitude of EMF, motional EMF important. Direction given by Fleming's right hand rule. Okay, BVL. Generally, people used to say this is BVL sin theta, but general formula is this one. Okay, so formula for EMF is very important. Here the electric field is not induced, but it is the conventional electrostatic field produced by moving conductor when conductor is moving. This EMF does not produce any current here because circuit is not complete. If you make this circuit complete, if you complete that circuit, I will draw here. You complete that circuit like this. Complete that circuit like this through an external load R. Then E stands for motional EMF, P and Q. P below, Q above. The magnetic field was inward. Velocity was rightward. Now that produces a current directed from P to Q inside that wire and Q to P outside. And this is the conventional current. That current can be BVL divided by R. Okay, then that produces a current through that. That current is I. Now this is a current carrying wire in magnetic field certainly acted upon by magnetic Lorentz force. Still Fleming's left hand rule. For finger inward, middle finger, see, current. Fleming's left hand rule for finding magnetic Lorentz force on a current carrying wire in magnetic field. Thumb magnetic force. Magnetic force is directed towards left. Okay, and that magnetic force would tend to act against the proposed direction of velocity. That is why to make the conductor moving with constant velocity, external agency is to exert hard. To make this conductor move with constant velocity, external agency to supply some mechanical extra force. That force is given by B, I, L. Substituting for I, you get B square, V square, L square divided by R. Sorry, B square, L square, V divided by R. B square, L square, V divided by R. Only one V comes there. But that needs a mechanical power consumed that is equal to B square, V square, L square divided by R. So power needed to make this conductor move constant velocity. You cannot accelerate. If you try to exert more force to pick up more velocity, it is not possible. Why? When you try to increase its force, then current also proportionately increased. That's why you can keep it moving with a constant velocity. Whatever velocity you started to make it move, then you can continue with the same velocity, that's all. The initial velocity with which that conductor was entering this magnetic field can be continued by supplying an extra force and thereby consuming a constant power. That is B square, V square, L square by R. Power proportional to B square, power proportional to V square, L square by R. This topic is very important. Motional EMF. And this mechanical power supplied is completely utilized in heating this circuit. But from Joule's law, this mechanical power can be equated to the Joule's power. Mechanical power and Joule's power are equal. That means energy conserved. So it is never against conservation of energy. Lenz's law, as well as the development of power in motional EMF, is not against conservation of energy. That's very important. Now, motional EMF at the ends of a conductor rotating in a magnetic field. If a conductor is rotating in a magnetic field like this, rotating in a magnetic field, conductor is rotating in a magnetic field. A conductor is rotating in a magnetic field about a vertical axis passing through its center and with constant angular velocity omega, length of the conductor is L. Direction of magnetic field is upward. Magnetic field direction upward. At this end has a velocity V at this instant. Rotates about that. Length is rotating. Then the voltage developed at the ends P and Q is equal to, you can use half B L square omega. This also is BVL. But the problem is that V is not a constant. At every point V changes. V is maximum at the end. V0 at P. Fixed axis rotation. V equal to R omega you can use. That is why you have to take the average speed of the velocity varies linearly with the distance. you can take V by 2. So half VBL, half BVL. BVL by 2 is the answer. BVL by 2 is this one. BVL by 2. That's why that may be a probable question, that a conductor of length L is moving in a perpendicular magnetic field. The induced EMF is, motional EMF is 10 volt. Now one end is fixed and the other end is rotated such that the tip of that wire has the same speed as the center of mass of the wire. Then that voltage developed is exactly half. Half BVL is written as half BL square omega. It's very important topic. Formula for induced EMF at the ends of a conductor rotating in a magnetic field. To identify the polarity, you can use Fleming's right hand rule. Magnetic field is upward. At this instant, velocity of the tip Q. Hope you following. Magnetic field is upward. Middle thumb represents velocity. Velocity is along Q. Tip is moving inward at this instant. So now motional EMF is given by middle finger, that is towards the right. So EMF is from P to Q, that is P minus Q plus. Okay. There is no current if there is no closed loop. If there is a closed loop, that can generate a current. That's it. Okay. So induced electric field, induced voltage, induced current, induced EMF, then induced charge, motional EMF, all this. Now, inductance, self-inductance, letter L, self-inductance. Inductance, what do you mean by inductance? Is the phenomenon by which a coil opposes growth or decay of current through it. The formula for self-induced EMF in a coil is minus L di by dt. The total flux linked with a coil N phi is equal to Li, where L is equal to N phi by I. Its unit is Weber per ampere or Joule per ampere square. So dimension is ml square, T raised to minus 2, A raised to minus 2, Joule per ampere square, scalar. Inductance depends on only the geometry of the coil. When you double flux, current also doubled. So flux per current is a constant. L is a proportionality constant. It's a scalar. This minus sign is given by Lenz's law. If current is a constant, voltage is zero. This is called a self-induced EMF or back EMF. Back EMF is the reason why a spark is noticed at a plug when switched on. That is self-inductance. Unit, dimension, it's a scalar. Back EMF equation, flux equation. Inductance of a solenoid can be developed from this equation, which you are familiar. Mu 0 n square Al. Mu 0 n square Al in air cored solenoid. If a medium is soft iron core is inserted, that becomes mu 0 mu r n square Al. So on introducing a soft iron core, inductance increased by a factor of mu r. Again, mu 0 mu r n square A divided by L. Another one, mu 0 n A n, where small n equal to total number of turns per length of the solenoid. Solenoid we have already seen in the last chapter. Moving charges and magnetism. L is the length of the coil. Total turns is n. Total turns by total length will give turns per unit length. So self-inductance of a solenoid as well as back EMF. Now energy in inductor is given by magnetic energy, that is given by half L I square is the formula for magnetic energy proportional to I square. On I, when doubled, energy becomes 4 times. I increased by 10%, energy increased by 21%. I increased by 20%, energy 44, 30, 69, 40, 96, 50, 125, like that. There is a shortcut that we have already discussed. You can try it later. U proportional to I square, U proportional L. It's very important. Now energy density. Energy density can be written using this cursive U, that is UB divided by volume. Energy per unit volume of magnetic energy per unit volume. That will be B square divided by 2 mu 0. Energy density. So magnetic field has magnetic potential energy. and magnetic potential energy per unit volume is given by V square by 2 mu 0. This is also very important. Okay. Self-induced EMF. What is that? When a coil is there, the coil itself carries a changing current. Coil itself carries a changing current. That changing current in a coil develops a change in flux in itself, which thereby producing an induced EMF which opposes that change in current. Okay, that effect is called self-induction. The same coil's rate of change of current produces EMF, but that opposition is produced by a change in current in the neighboring coil. That effect is called mutual induction, and that proportionality constant is mutual inductance. For example, if the first coil N1 is the flux linked with the first coil, due to the presence of a second coil. So N1 is the flux linked with the first coil when a current is passing through the second coil, and that current is changing in time. N1 is proportional to I2, that is N1 equal to M12 I2, where M12 is the mutual inductance of the first coil with respect to second coil. Similarly, N2 can be written as M21 I1. This is also important. Okay. For reciprocity theorem in electromagnetic induction, it can be proved that M12 equal to M21, for which there should not be any flux leakage, for which the two coils should be wound one upon other, which is done in a transformer to minimize flux leakage loss in a transformer. And that reciprocity theorem says that M12 equal to M21, then that can be written as M. Formula for M is mu 0 mu r N1 N2 pi r1 square L. Mu 0 mu r N1 into pi r1 square L, where R1 is the radius of the inner coil. There are two coils of radii R1 and R2. R1 is that of inner coil, where we have to take the common area A1. A1 is nothing but pi R1 square. That part is very important. Notice it. N1 and N2 are number of turns per unit length for each of the coils. But pi R1 square or A1 area, chosen area should be the common area or area of the inner coil. In a transformer, primary coils are there serving as the inner coil. Secondary comes outward. Secondary wound over primary tightly so that there is no flux leakage. If there is no flux leakage, this reciprocity theorem can be applied. Therefore, if L1 and L2 are self-inductances of primary and secondary, then you can choose square root of L1 and L2 as mutual inductance. General formula for M is K root of L1 L2, where K is a coupling coefficient. For no flux leakage or for no flux lost, no energy lost due to flux leakage loss, or for a tight coupling between primary and secondary, you can choose K as to be 1. Then mutual inductance has its maximum value, that is equal to L1 L2, root L1 L2. K is 0, that is the minimum. No mutual inductance. That is, field lines of first coil does not cut the second one, then mutual inductance becomes 0. If K equal to 0, mutual inductance is 0. So K value can vary between 0 and 1. K value has maximum 1, minimum 0. For tight coupling, K is 1, M is equal to root L1 L2. Okay, that is mutual inductance. Mutual inductance also has same units and dimensions as that of self-inductance. So its dimension is ml square, t raised to minus 2, a raised to minus 2, joule per ampere square. Henry is the SI unit of inductance. Henry. Okay. Joule per ampere square, that means Weber per ampere. Weber per ampere is also called joule per ampere square. Okay, this type of units and dimensions are very important for all these topics. So we have learned in this chapter. I will tell you the topics. So not a big chapter for quick revision. Induced electric field, induced EMF, induced current, induced charge, induced voltage, motional EMF, all formula. induced voltage minus d phi by dt. Induced electric field formula, Faraday's law, closed integral E dot dl equal to minus d phi by dt. Phi is the magnetic flux. Magnetic flux B dot A, Ba cos theta. Unit of magnetic flux is Weber, Tesla meter square. Dimension is joule per ampere or ml square, T raised to minus 2, A raised to minus 1. Magnetic flux is a scalar, but it can have positive and negative values. When magnetic field lines graze a given plane of the coil, there is no flux. Okay. AC generator works on electromagnetic induction, phenomenon by which there is an induced EMF at the ends of a coil whenever there is a flux change with time linked with the coil. The voltage in AC generator is time dependent V0 sin omega t, where V0 is the voltage amplitude given by V0 equal to BAN omega. Maximum of flux is BAN. Maximum of voltage is BAN omega. So that is also important. Maximum of flux is BAN. Maximum of voltage is BAN omega. So V0 divided by phi 0 is omega. So that V0 is equal to phi 0 omega. V0 divided by phi 0 is equal to BAN omega divided by BAN. That's omega. So V0 equal to phi 0 omega. So omega can be measured as V0 divided by phi 0. Omega is V0 by phi 0. Okay, that also may be an expected question. V0 by phi 0. Okay, omega equal to V0. Voltage amplitude by flux amplitude is the angular frequency. That's very important question. Okay, after that, motional EMF at the ends of a conductor rotating in a magnetic field is BVL by 2, where V is the speed of the tip. That is half BL square omega. Omega can be substituted as 2 pi by T. Direction of induced EMF given by Lenz's law, motional EMF given by Fleming's right hand rule. Okay, while applying motional EMF, Fleming's right hand rule, 4-finger magnetic field, hold your right hand. 4-finger magnetic field, thumb velocity and middle finger is EMF. But while applying Fleming's left hand rule for finding magnetic Lorentz force on a current carrying wire in magnetic field, there you are stretching your Fleming's left hand rule, you are stretching your left hand fingers. There 4-finger magnetic field, thumb is force and middle finger is velocity or current, whatever. Okay, after that we discussed the inductance, phenomenon by which there is an opposition offered by a coil whenever there is a growth or decay of current through it. Inductance, self-inductance, formula mu 0 mu r n square al, mu 0 n a n, mu 0 n square a divided by l, where n is capital letter. Or n phi by I, flux per current. Flux doubled, current also doubled, L does not change. L depends on the geometric parameters. The most important thing is that when a soft iron core is inserted, L becomes mu r times L proportional mu r. L proportional to n square, turns per unit length doubled, self-inductance quadrupled. L proportional to n square, turns per unit length increased by 10%, self-inductance increased by 21%. That type of questions are very popular and common. Mutual inductance formula mu 0 mu r n square, mu 0 mu r n1 n2 A1L, where A1 is the area of the inner coil. For minimizing the flux leakage, primary and secondary, one wound over the other, secondary wound over primary. Coupling coefficient is maximum 1, where mutual inductance root L1 L2 if K is lying between 0 and 1 for a real coil, not ideal. M equal to K root L1 L2. There flux leakage is there really, but ideally there is no flux leakage. There are many losses of energies in transformer. Very important losses of energy is flux leakage loss, another one Joule loss, another one hysteresis loss, another one eddy loss. So eddy loss, Joule loss, hysteresis loss and flux leakage loss. That flux leakage loss we study here. That are the losses of energies in transformers. Transformer works on the principle of electromagnetic induction or mutual inductance. Let us discuss the topic transformer in the next chapter, that is in chapter AC. We will be discussing transformer in AC, right? Because transformer works with AC only. Transformer, when you feed DC to transformer input, output would be 0. Okay. So we have completed the quick revision. Okay, see this, we are doing a quick revision, so I'm not going in detail as we do in theory classes. Also, you can make advantage of this so quickly. So I'm telling everything fast. You can repeatedly listen to that. If there is any doubt, you can ask also. Then we'll be meeting with the next chapter AC soon. Thank you.